In this lesson, we will determine limits at infinity using the highest degree term in the numerator and the highest degree term in the denominator. Looking at our first limit, where we have the limit of the rational function as x approaches infinity, notice the term with the highest degree in the numerator is 3x to the fourth. The term with the highest degree in the denominator is x to the fifth. The idea here is that 3x to the fourth is going to overpower minus 3x squared plus 8 in the numerator as x approaches infinity. In the denominator, x to the fifth is going to overpower 2x cubed plus 3, again as x approaches infinity. And therefore the given limit is equal to the limit of 3x to the fourth divided by x to the fifth as x approaches infinity. Notice here we can simplify. 3x to the fourth divided by x to the fifth is equal to 3 divided by x, giving us the limit of 3 divided by x as x approaches infinity. Whenever we have a fraction where the numerator is a constant and the denominator contains a variable that approaches positive or negative infinity, the function values get smaller and smaller and approaches 0, and therefore the limit of 3 divided by x as x approaches infinity equals 0. And the value of this limit is the same as the value of the original limit. Looking at the second example, the highest degree term in the numerator is x to the seventh. In the denominator, the highest degree term is 2x to the seventh. So again, x to the seventh is going to overpower minus 3x squared plus 8 as x approaches infinity. In the denominator, 2x to the seventh will overpower 7x cubed plus 3, again as x approaches infinity. And therefore this limit is equal to the limit of x to the seventh divided by 2x to the seventh as x approaches infinity. Again, we can simplify. X to the seventh divided by 2x to the seventh is equal to 1/2. If it's helpful, we can place a coefficient of 1 in the numerator. Simplifying, we have the limit of 1/2 as x approaches infinity. Well, notice 1/2 is not affected by x, and therefore this limit is equal to 1/2, which is the same value as the original limit. For the third example, the term with the highest degree in the numerator is 2x to the fifth. The highest degree term in the denominator is 9x cubed. And therefore the given limit is equal to the limit of 2x to the fifth divided by 9x cubed as x approaches infinity. And again, simplifying, we have the limit of 2x to the fifth divided by 9x cubed is equal to 2x squared divided by 9, if we want 2/9 x squared, as x approaches infinity. Notice as x approaches infinity, the numerator increases without bound, the denominator stays 9, and therefore the values get larger and larger and approach positive infinity, and therefore we say the limit is equal to positive infinity. Just remember, infinity is not a real number. This really indicates the limit doesn't exist. But since this limit approaches infinity, so does the original limit. I hope you found this helpful.